it's not often we get back to the basics on PVC. So, sometimes there's just stuff that comes up that's kind of interesting as we're going through it. And I'll try to add the tidbits I can as we go. One thing I would say, I'll kind of pump it at the end as well. My colleague, Robert Nubli, is here as well from France. He's going to be giving the second webinar in July on impact modifiers. I'm going to have him join me for the Q&A as well, just so you can kind of have both of our brains to pick then at the end. So the first thing I would say about the format, I'm going to start with an intro into PVC gelation theory and talk a little bit about PVC itself. Obviously, there's folks that are probably here from PVC companies themselves that can go into much more depth in this, but the idea is to pull ourselves into why PVC is unique and why we have to process it the way we do. And if you've ever been excited about brave enders, today's your day. We'll talk about torque rheometers and some of the rheology and things that are interesting about PVC that differentiate it from other resin types. On the formulating basics, something I've always wanted to do but never had a chance to do in giving one of these talks is actually go into the idea of connecting gelation, PVC lubrication, some of the things we do with acrylics and modifying rheology, and then why, when we put them in the formulation, it becomes so important to think about how we blend them, why we're blending them the way we are, and what we're trying to get from the components when we actually make these formulations. Lastly, something that's a little dry, but I think can be important, is some PVC formulation examples. I kind of have them sorted by market and type and kind of go through the differences that we can see at a macro level of what changes as you go into different PVC applications and building materials. And it's kind of a guidepost for us to talk about if there's troubleshooting that comes along, what are the main things that come as you go through different building products. The only place I want to talk a little bit about Arkema is here. The reason I do that is because we are a supplier of acrylic modifiers and MBS modifiers. I think it's important for you to know that that's where my background is coming from as we talk to you about this. That said, I think, over the years, what I found is it takes a village in terms of formulating to make things work. You're never going to see one component be the only thing that'll solve your problem in most cases. As you change components, different things are going to happen that are going to affect and influence other things that are in the formulation. And typically when we try to do things a little bit more holistically, we get a better result. So full disclosure, yes, we supply these kind of modifiers. That's kind of where my expertise lies for a decade now. But I think that if we think about what we've been trying to solve over the years, you'll see that it's a part of the puzzle when we're trying to solve problems. So the first thing we're going to start with is the basics of gelation. And I have to say, not being a chemist, I'm a material scientist. I've been fortunate to speak with many good colleagues over the years who have become mentors of mine. And they would always start with this because I think when we think about VCM and the things that happened early on in the industry to save it and make it safe and make PVC as prevalent as it is as a building material, it starts with something that honestly is pretty dangerous that everyone is always worried about. And, it's pretty simple, right? It's a vinyl monomer that has a chlorine attached. That labile chlorine, when it's in PVC, is kind of the thing that can make this thing strong, but also cause a lot of problems when we're trying to formulate around it. So when we start with that basic building block and we look forward, very simple, polymer science 101, we do a free radical polymerization, and we build a chain where we're basically putting the VCM in to make PVC. And obviously this eventually leads to termination, and we can control the molecular weights, which I'm not going to go into too much detail on, but this is your basic polymerization reaction. And I think, something we don't always talk about is why PVC is as good as it is. The chlorine is big, it likes electrons, and the thing that happens in addition to a little bit of crystallinity, which is important, is it also has some really nice secondary bonding. And so we get a lot of good strength in the final PVC part because of the structure, because of the chlorine that's in there. And that's what makes it unique at the end of the day, is that you're using something that has this inherently strong bond whenever we process it, but process it correctly, right? And so I think, from a basic chemistry point of view, we're starting with something that's very strong, that wants to work very nicely in its polymer form. The main PVC resin processes that we've seen over kind of the history of the product being used, majority of it is in suspension PVC. This is the PVC resin that, if we think of pipe, which uses by far the most for B&C applications, window, even PVC foam and other building and construction applications, this is the main PVC resin. Mass resin is something that is still out there. So this is where, instead of being in a suspension process, you have the PVC actually made in its own monomer, and it leads to a different morphology of the PVC particles. So we're not going to talk about that specifically today. It's a little bit more specialized, but we have had customers over the years that use it, and it has its own unique requirements for formulation. And then lastly, emulsion polymerization. So the emulsion leads to basically a primary PVC particle that's already broken down and ready to use. When we think about what that could be as plastisols, dispersion resin applications, and some flexible applications that require, more fine application space rather than rigid PVC or semi-rigid. Again, today we'll mostly focus on suspension and rigid, but there are these different kinds that are out there that go to different applications and specialty applications as required. For suspension PVC, most of you have probably heard that we always talk about things in terms of K value or IV. And really, I would say that K value is something that most people know, but the IV is really the thing where we use dilute viscometry to specifically measure exactly what the molecular weight of the PVC is. There's ISO standards for it, ASTM standards for it. It matters when you measure the molecular weight that you use the right solvent, and that you do the test the same way under the same temperature, using even the same capillary to do that. So the people who make PVC resin, this is 101 stuff, and for them, very important. When we think about what a pipe might use for like an IV91 versus some flexibles that use a much higher molecular weight, that might be higher than that, or in foam where we use something lower, where we're trying to take advantage of expanding the PVC with blowing agents. You can see the range where you can have the IV become important. The initiation in terms of the monomer phase, typically we aren't too worried about what sticks around from that point of view. The residual things that come in the PVC that have some influence on additive performance or applicative performance down the road can affect things like heat stability, color of the resin, haze. I would say when you're selecting your resin, and you speak with a specific company about what their resin types are, it's important to let them know what your final application will be. That can influence what the color could be and how important the color is to you. And even changing seasons. We know that, when we're going between summer into winter, things that have to be put into the resin to keep anti-stat properties in check and things like that can change. That can influence your processing if you're making windows or foam or something like that, how it's stored in your silos. All of that can come into play and be kind of subtle. The thing that I say as an additive person, because it's easy for me, PVC, if we're talking about a rigid application, if we exclude flooring, it's still 80% of the formulation. So it should have an outsized influence on what's happening. So I'm lucky to have worked over time with Bob Paradise, and I've heard this said many times, but I think it's always something I come back to, is the PVC is the one thing that basically after you take it out of the reactor and dry it, you could basically take that and put it right into the extruder and use it to make whatever you're going to make. We don't have to pelletize it. We don't have to put it in some other form. You can basically take the PVC just like it comes out of the suspension process, put your additives with it, put it in the extruder, and you're good to go. And this is probably, for me, why it becomes so important and why it's still used so widely. It's just easy to imagine how you're going to use it. And obviously, this also means that in PVC world, often we're a powders business. We're a white powders business. In engineering polymers, my colleague who manages things on that side, they get really afraid of white powders. We live in a white powder world. Everything we do is a powder of some kind, right? And being comfortable with that and understanding how to utilize it correctly and process it is important, but it's also kind of the ease and the pathway to using it so widely. If we look at the suspension PVC particle itself, I think this is where PVC starts to already deviate from most thermoplastics and why it's unique. So this is kind of a cross section. So if you can imagine your PVC particle and we cut it right down in the middle and we take a look through it, what are we seeing? So a PVC powder particle itself is somewhere probably between 100 to 200 microns. I'm sure I can get corrected on that on the specifics of where it needs to be. But if we think about formulating, the very first thing we think about is the powder particle itself is 100 to 200 microns. Every powder you put with PVC as an additive probably should be somewhere around the same size. We don't want to segregate. We don't want it to look different than the PVC when we put it in the mixer. We want everything to be compatible so that once the dry blending is done, we have something that's homogeneous and will flow and convey really nicely. So that's the first thing. PVC is 80%. You want things to match kind of that primary particle size of the powder. As we go deeper and deeper into the PVC particle, what you see that's unique about it is the skin that forms around the actual powder particle itself. And inside, we have essentially these primary particles. So we'll call them 1 micron primary particles. But these are kind of the keys to unlocking the success of how PVC can be processed. We need to essentially break that skin, release these primary particles on the inside, and eventually, after all that's done, get all the way down to the polymer level where we're actually getting entanglements of the PVC polymers. And this is where it becomes important of how the chlorine and the secondary bonding takes place, start to have some crystallization at a low level and some structure forming inside to build on the properties of the PVC itself. If you look at the PVC under a microscope, so this is something that, I mentioned Bob Paradise and others have talked a lot about. It has this wrinkled popcorn appearance. As it goes in the suspension process from basically the droplets that are in water versus the final particle that's being polymerized, you see this change in bulk density. And so that change in bulk density leads to this craggy popcorn surface. This is a bonus. That means there's high surface area. There's a lot of room here for stabilizers, lubricants, and plasticizers to actually integrate into the PVC once it swells under heat. So this is actually a good thing in terms of how the morphology defines itself from the process. When we get to thinking about what gelation means, I think the first thing I would say is I always talk about gelation different from fusion. So I think for this talk, I think it's important for everybody to keep that in mind. Gelation is what we're going to talk about here and how we utilize the PVC particle and structures that are within it. Fusion is something that we're doing in processing to make sure that we're getting in the right direction for the final part that we're going to make. I'll explain how those two come together, but the idea of gelation versus fusion is, I think, important and a fundamental thing that can be confusing sometimes, but what we're actually trying to get at for making a good PVC product down the line. Gelation itself is breaking down that powder particle and releasing those primary 1 micron particles on the inside. Eventually, the next thing we're doing is having the entanglements of the molecules themselves. And that is the process of gelation. Now, you can get different levels of gelation. You can break apart the powder, get the primary particles released and not get a lot of good entanglement of the primary molecules that are actually PVC of some molecular weight and K value. Or you can get a very, very good integration of those and have a very high gelation level and understand how that might affect your product as well. But what Summers does when he makes this model is he basically tells you that there's inherent limited amount of crystallinity inside the PVC already after it's been made in the suspension process. We're able to take those primary crystallites and begin to melt them a little bit. Basically loosen up those primary particles once they've been released from the powder particle. Re-entanglement of the primary molecules can then start to occur, get secondary crystallites as we start to cool the material after it's processed, and have a 3D network that essentially builds towards what we're getting at for your final properties. So this isn't something, where I've worked with PMMA and polystyrene and other things in the past that are mostly all amorphous. You actually can take advantage of this limited amount of structure that's built in from the chemistry and the reason why PVC wants to have this other secondary bonding that's very strong, and build a structure within the PVC that gives you the final mechanical properties that enhance whatever the properties are you're looking for in the application. And to me, this is kind of the thing that makes PVC unique, but also makes it a little bit of a dark art. And when people say it's a science in formulating, this is pretty much what they're talking about. Just getting this piece done before you do anything with the additives is not a foregone conclusion. And the people who do it the best and understand how to do this are typically the most flexible when it comes to formulating and changing things. Now, if you've ever done anything with a braid bender, or if you're new to PVC and you're just starting to use a braid bender, I will say that I'm just like you, and this is the first thing that I was taught how to do, is to use a torque rheometer. So, you know, braid bender, hockey, there's the different brands that are out there. The basic idea here is we have two paddles, we have an enclosed controlled volume, and all we're trying to do is mimic one cross section of an extruder. So if you can think of an extruder with long screws going down the barrel in a twin screw fashion, and we basically, just like we did with the PVC particle, take a cross section of that and cut it out. That's basically what your torque rheometer is. You're taking a small section, doing some mixing and trying to predict essentially how your PVC compound will act, fuse, how stable it can be, how much torque it can generate when you modify it with different additives, even how much degradation you can see in real time. And it's a very simple tool. You know, I always tell people it's a dumb tool. It's going to turn on, it's going to work hard as you tell it to, get to the temperature you tell it to, and what you take away from it and how you modify your formulation is totally up to you. But it's going to do its job. It's going to turn the paddles, and it's going to tell you how hard it is to turn. One thing my colleague had shown me long ago that I think is just the best, frankly, is this video of real time of what's happening when we're looking at a torque rheometer and what it's actually doing in real time. So this YouTube video, oops, see if I can get to play here. This YouTube video is one of my favorite things. You know, literally what we're trying to do here is show you in a braid bender peak what's going on in real time. So we have powder. Right now, we've basically compressed it into the bowl, and we're working towards fusion of the PVC. And then as we go through the powder actually interacting and becoming fused, we're working through the gelation process at this point. We're starting to build that 3D network because we're getting more entanglements of the primary PVC particles. And basically through the processing time here, which we're mimicking for an extrusion process, we're trying to see, okay, how high of a torque do we get? And then you can see at the end there was even, I'll play this again just for the sake of doing it. You can see at the end there was even a ramp up in the torque. And sometimes that can be an indication of degradation, or when we push the material too far and put too much heat and work into it, and the PVC itself starts to degrade or cross-link. So this is the basics of, I think, where just about everyone starts in the PVC lab. You take your powder, you put it in the braid bender, see what you get on the other side, right? What we want is to start with the powder, compact it, go through fusion, get good gelation. And when we take it out, you know, we take our glove, we see what's in there. You have this banded melt of PVC that's fully formed, fully homogeneous, hopefully white, if that's your intended color. And you can basically see that you've made a nice, you know, PVC article with the settings that you have. What that looks like as we go from a microstructure evolution point of view is, again, thinking about it in terms of gelation. We are trying to start with these primary PVC particles and eventually break them down and have interaction of the molecules themselves. And so you can see the main idea of moving from the powder and the powder that's in the dry blend through the process of fusion, which is, I think they have it 180 seconds or so, is compacting the powder, starting to break down the skin, opening it up and having the primary particles come out, and eventually moving towards a continuous melt where we've had the primary particles interact with each other and now molecules fully forming, getting a 3D network. Once this cools, getting your secondary crystallite formation and having a nice strong PVC article that's well processed for the targeted application. On a macroscopic level, what do you see? If we stop the bowl and do a simple experiment, right? These are simple pieces of equipment. We can stop the test anytime we want. We can pull the bowl apart, and we can basically see what's inside. So we put in, obviously, a powder to start. 30 seconds after we do that, we can get kind of a chunky powder that maybe has a little bit of loose aggregation. A little further along, after we've compacted and started to break things apart, we get something that's a little more formed right around the fusion point. So this is where people will tell you to look in the vent. We hope that we get something that's banded and more or less associated. And as we go further along, you can see this is a clear without any pigment of any kind. You get essentially a fully banded PVC article. This is, you know, depending on how you look at it, where you're trying to gauge how your PVC is processing. If we go and think about that, then in the longer case where we take away from a cross section of the screw and we go out to the full screw during the flights, the same process is happening, but now we're conveying the material from the hopper to the die. The process now has to take part along that extruder barrel and essentially do the same thing, except staying in one stationary place, we move along the barrel. And so it's the same idea. This is all what we're trying to do with this very simple piece of equipment, the torque rheometer. I always tell folks, don't underestimate how you can use it. A simple brave ender test, just to test where your fusion peak is, where you see any kind of degradation beginning, how much compaction, what your bulk density looks like. Okay, bulk density is important. The brave ender is a controlled volume. You are supposed to, according to the ASTM standard, put in a controlled volume, not a controlled weight. If you change the amount of filler, amount of TiO2, what kind of process aids you're using, how much PVC is in there, the bulk density will change. When you test, you want to make sure that you're always testing for the same volume. That's kind of the like. And that also helps you mimic if you're controlling the feed into your twin screw and you're star feeding it in some way and not flooding it. That's also important because, again, it's a controlled volume that's hitting those screws versus what you might be doing with an actual weight of material. So the test that we do off of that, I think you saw some of it. Expanded fusion. So this one I wouldn't necessarily, I'd probably want to draw this out a little bit more. But the idea here is to look specifically at the fusion peak itself. So this is where the material is more or less aggregated and agglomerated. We have a good association of the primary PVC particles that have been released from the skin. And we try to see, okay, what's the difference in fusion time between two compounds when I make adjustments? Very simple. We take a look at that, we draw it out. That's why it's called expanded fusion, and take a comparison. The other tests we might do, especially for stabilizer and lubricant folks, is we want to see what kind of thermal stability we have. And so what you're looking for here is kind of where you start to see a degradation at the end, a fall off in viscosity, or like I said, sometimes it can actually start to increase. That can be cross-linking that the torque is finding when you're trying to turn the paddles. But you'll see that here, because you use a higher temperature and maybe a higher RPM, because you're trying to accelerate the test at this point, now all of a sudden you get a much more compressed fusion peak, and you're worried about kind of the long-term equilibrium torque and where that degradation occurs. So two different ways to look at it. I can tell you that there are a million settings in between where you can look at it. Every company may have their specifics where they find this is what we need to know to understand the changes in our formulation. So I encourage you, if you're new especially, definitely play with it. Definitely try and do your best to see how you can modify it. And I think what you'll see is you'll have a lot of interesting ways to look at your formulation you hadn't thought of before. So the next thing we're going to go into is a little bit around the formulation itself. And like I said, I want to start with some of the basics of just why do we use lubricants? How do we balance them? So the same guy that came up with their gelation theory, Jim Summers here, I have kind of his lubrication theory. And I think this is a good place to start because as much as I, as an acrylic supplier, always want you to use acrylics for everything you do, basics of what you really need in a PVC formulation most of the time, and pipe's a good example, is the PVC resin, the stabilizer, and then the lubricant set. That'll get you most of the way of where you need to be to make a good PVC article. The other additives that come in after that are typically application specific, where you're trying to tailor properties very specifically and enhance mechanical properties in some way, or how the article may perform for a given application. When we look at the basics of lubrication theory, I think most of you have seen over time, it's a combination of paraffin wax and calcium stearate. This magical, two things that we put in opposition of each other. The paraffin is your lubricating, your external lubricant, and the calcium stearate, while lubricating, is thought of more of as an internal wax and doing most of the work to incorporate the PVC with each other. In theory, what's happening is when you do the PVC by itself, you get these primary PVC particles. They might interact a little bit, but they're probably going to start to burn and break down before they actually form a 3D network. If we just use calcium stearate, you can kind of have this extra layer of lubrication where, again, you may prevent the PVC from interacting nicely with itself and forming a 3D network. And you might, again, get burning. It's more of an internal lubricant meant to enhance fusion rather than prevent burning with metal. If you just use paraffin and we over lubricate, we all know that that can lead to the same issue where, again, you don't get good gelation. Now you have a lot of metal contact with the lubricant, and we can think of almost like a tube flow with toothpaste. You kind of just push everything out of the barrel, and there's not a whole lot of mixing in between. The key comes when we actually mix the calcium stearate and paraffin together, and we find that we can create these slip layers with the paraffin. The calcium stearate has both the polar and non-polar ends. We surround the PVC on the polar side, and we get this balance of interaction where we now have a good interaction of PVC primary particles to break down into molecules, good balance of lubrication with metal surfaces, and overall then can make it through the extrusion process at high heat without degrading the PVC, which, because of the chlorine, always wants to degrade where possible to pull those chlorines off and make HCl. The thing that's cool here, like over time, I think someone had told me that 1 PHR is kind of what you always see for calcium stearate. Someone did the calculation on the surface area of a PVC particle, and it turns out 1 PHR, if you look at the full formulation, is the amount of calcium stearate it takes to cover the surface of PVC. So now you can see it's optimized. You tailor it with the amount of paraffin wax, and you kind of get the ideal situation. What this means to me, if I go back to the gelation and what we looked at with the torque rheometer, is that you're doing the same thing now. And with just your paraffin wax and calcium stearate as an example for lubricants, you can start to take notice in your extruder where you want things to happen. And if we think of, again, the fusion and gelation process and those two different things where gelation is actually starting the 3D network, but we're compacting the powder, we're starting to get association and aggregation, and then fusion might happen somewhere around our vent port. So we get something loosely aggregated, associated. I've always been taught it's like cottage cheese, but really when you look in the port, it's depending on what you're making and how aggressive you are. You may see something that's like a rubber band stretched around the screws, or you might see something that looks like dough kneading that's less developed in terms of the melt. It all depends on what you're trying to make in the speed of the extrusion. So it's totally up to that application. Regardless, you're using your lubricant package to form that process in the vent and where it takes place on the screws to control it. And by the end, you want to basically be able to extrude something in the die that is exactly what you want to use, so that after it cools, you have the best mechanical properties, surface finish, color, etc. So we're all working towards the same goal. Again, it's all coming to the same place. When I think about how we modify those two things, things that can be done that are kind of interesting, we can look at different paraffin waxes. So I'm sure that there's folks here from lubricant supply in some way or another. No, not all paraffin waxes are made the same, okay? So we have some that are refined, they're very high melt, and some that are low melt. And you might say, why would I want a low melt? That's cheap, it's not gonna work. Well, a low melt wax, if used properly, can be fusion promoting and still give you lubrication. A refined paraffin will certainly decelerate fusion time, but if you have something tricky with tooling where it's very complicated and generates a lot of high shear with your extrusion process, it may save your bacon and prevent the PVC from burning before it leaves the die so that you don't have poor weather. All of this is here to say that you may use, these are, I think, all at 1 PHR of the paraffin. maybe you can get away with 0.6 of a refined paraffin versus 1 PHR of a low melt, and start to make the balance right for your equipment set and your application. So it's important to keep that in mind. The other thing is, if you're getting a paraffin wax and you do a melt temp on it, how many peaks do you get? Do you get one? Do you get two? Do you get more? That gives you also an indication what the makeup of the waxes you're using. If there's some low melt mixed in with high melt, you might see some inconsistent fusion depending on how that blend comes to you lot after lot. These are things that you can kind of check on your own and aren't too difficult to do. Same thing goes for calcium stearate. Again, it's a lever. The more you use, the faster your fusion generally gets, because we consider this an internal lubricant. That said, I think after 1.5 PHR, I have tests that are in the same study I'm showing here, where you get kind of diminishing returns and you flatten out. And if you have too much calcium stearate, it can lead to bad things. So you start to prevent good processing. You may interfere with other additives, or the dry blend itself can start to be impacted in terms of how nice it is and clumpy it is. That said, you can go probably too low as well and not have the good balance between the paraffin and the calcium stearate for what you're trying to do. Now, beyond these lubricants, there's obviously a library of them, from esters to complex esters, even mineral oils and other things. ESO can be used as kind of a co-stabilizer. So, once you get into this and you start to see how many options there are, it's kind of endless. For me, I like starting with the basic building blocks. Typically adding things makes it harder to take them out later, but there is a time and a place for some of the specialty lubricants to get you some special processing that you might not get otherwise. If we look at other ways where we're modifying gelation, one of the other areas is thinking about what you might do with acrylics in the formulation. So one of the main ones to boost fusion or boost gelation time is obviously a process aid. When you use a process aid, today we think of all the ways that you can use them. We have film and sheet applications, we have window applications, you have flooring applications with high filler, you have foam where you need to make cell structure. When we started using process aids, the goal was one thing. It was force and shear transfer between primary PVC particles, okay? So once we broke that skin open, what we wanted to accelerate was the interaction between those 1 micron particles and make sure that we were, as quickly as possible, getting molecular level entanglements. That was the initial goal. Now, today, you have molecular weights that go, I have hundreds of thousands here to greater than 10 million. I mean, the options you have in between, the way that you can change the chemistry, all of that is very complex. And all of it helps accelerate fusion. So generally, if you're putting in acrylic in your formulation, there's only a handful that are probably pretty fusion neutral. The rest of them, I would say overall, what you're going to see is increasing torque, increasing fusion promotion. And you have to monitor that, right? Because if you add too much and you do this too much, you can lead to back end burning and things like that. Torque that's too high can be hard for the equipment to handle over time and wear on the motors. So there's a balance for everything, and there's a place for everything. The other piece of that is that obviously impact modifiers are used for some applications. Well, an impact modifier essentially is a rubbery core. To make it compatible and be able to be dispersed in the PVC matrix, we have a mostly PMMA outer shell. PMMA, very miscible with PVC, typically fusion promoting. And so you can see same thing as we increase the amount of impact modifier in formulation. And this is something Roberto will go into further in the July talk. Essentially, you start being fusion promoting as well, and you can change the rheology of your formulation. So all of these different levers, when they come together, are things that you have to think about when you're trying to modify a formulation. One of the most common that I've seen over the years, obviously since the 90s going into the 2000s, was the idea of low rubber versus high rubber impact modifiers. So what would that help us do? It would help us reach our optimum and mechanical properties and impact strength. But now with less shell content, we were changing the rheology of the overall formulation itself. So while we might, with more efficiency, meet our impact levels and have a very nice performing mechanical property, we might have more difficulty in terms of what the fusion time looks like. You might change the surface finish because there's less acrylic in the formulation. It might not be as glossy, right? All kinds of things that can be affected just by changing something that you would think isn't really there for that purpose, but has a very big impact in the end on everything you're trying to accomplish with the balance of properties of the final article you're trying to achieve. So one other thing I would say, and flooring is kind of a special thing, but I like it because it's so extreme in terms of the level of calcium carbonate content. Here is a very good example where, in a semi-rigid formulation, because you have plasticizer content, it should be easier to fuse because it's swelling the PVC, it's helping to basically break down and interact easier, but you've added at least 250 parts of calcium carbonate. Now, when you do a fusion test, getting the consistency of a sample to sample lot is a little bit of a, roll of the dice. What we can easily see is when we add just a little bit of process aid to that formulation, by percentage, very small, maybe 1% compared to 350 PHR in the total formulation, our batch-to-batch consistency in terms of the processing becomes much, much higher. And if you consider further that this might not be done on an extruder, but a Banbury mixer and put on calendaring rolls or a planetary mixer and then sent through a calendaring line, it's even less shear than you would normally see. And so the consistency is valued because now you're high speed processing and making a lot of product, and you need to be consistent batch to batch. So I would say this is one area where you can kind of see the effect of what a process aid would do. But similarly, I could use the same example for window profile, where we go a little hot on paraffin wax and go high with the refined wax. We have some issues with mechanical properties. Maybe the impact's a little low. We pull back the level. We still get some good fusion, maybe even a little bit faster fusion. Get a little bit less on the metal release and the back end stability, but you're still in the color zone. You get better mechanical properties because you're more dialed into where the gelation is actually meeting the fusion properties and then the impact strength. If we think about the holistic formulation and kind of the basics, I think it's important, again, I'm coming from a rigid point of view here for the most part, so I think that's easier to start with. There's still a lot of things in the formulation. What did I tell you? The PVC, the stabilizer, and the paraffin calcium stearate combination is probably your basics to get you going. And then after that, you're worried about what your final application is. Do you need process aid for even more fusion promotion? Is it a calendaring line where you have a very, very high surface area sheet and you need melt strength so you don't have sag? Is it for foam where you want to have a cell structure that's dialed in and you need the actual process aid to stretch along the molecular direction as you have a nucleation site and an expanding bubble? Okay. Is it something for window profile, siding, fence, where you need impact resistance and your impact modifier is going to help you provide some durability? Filler content, how much can you add? How much will it hurt you? Will it affect weathering? And then, of course, your pigments. TiO2 is the main one for weatherability. I think it's the rutile phase that gives you the best light-free reflectivity there. But protection from UV for PVC is very important in weatherable applications, obviously. What you'll notice is that I have everything listed in a specific order. This is on purpose because there is a blend order that we're supposed to adhere to. A lot of times over the years, I could say that this is not how everyone does everything. There are PVC compounders who are experts at making good PVC compound that looks like the one with the green check mark there. Nice, flowing, easy to convey, okay? No clumps, no golf balls, no softballs. That's what we want to make. There are people who know how to get around this order and still make something that look nice like that, right? But what we're trying to do when we think about the PVC, I mentioned we have this popcorn structure with high surface area. The first thing we do is we put the PVC right next to the stabilizer, whatever that stabilizer type might be. Why? The PVC will start to expand around that 150 F range. It will become porous. It will take in the stabilizer. The stabilizer and the PVC being next to each other is the most important. The whole job for the stabilizer, whether it's calcium, zinc, or tin, is to coordinate and ensure that they either capture a chlorine that's pulled off from becoming HCl, or scavenge it in some way and make sure that it doesn't lead to conjugation of your backbone. In the case of tin, it's inserting, and in calcium zinc, they're actually inserting some kind of ligand in the backbone and stopping you from getting 6 to 7 conjugations, which will start to give you yellowness. That's what we're trying to prevent. After that, you see lubricants and plasticizers are coming next. Again, you want those next to the PVC because that's what you're trying to protect as you get through the extrusion process. Tin stabilizers will not help your weatherability, or well, they can affect it, but they're not primarily there to help your weatherability. What they're there to do is protect you during the processing so that at the end, you have as little degraded PVC as possible so that it will weather as long as possible. It's not just thermal heat that's going to help degrade your PVC. Remember, it's the UV light that comes after. So as pristine as you can get that PVC by the end, you're going to be in good shape. After that, you can see I have the acrylics and fillers, TiO2. You go to some temperature around, the boiling temperature of water. We want to drive off as much as possible, and then we cool it. Obviously, there's specifics for your blending capacity and how you would fill it up based on manufacturers, but this is the basics, right? The list and the order is important because it's getting you there to the place you want to be for overall the best possible outcome when you go to extrude and process. So I have this as more of a takeaway slide for people who are interested afterwards, but there are some things that can happen if you decide to disengage from your recommended blend order. The thing I would say that probably comes up the most is where you put in the calcium carbonate. There are folks who want to basically, after the stabilizer, put the calcium carbonate in next to try and get it as dispersed as possible, and they put the lubricants in afterwards. Lubricants go on the calcium carbonate, you convey, and you get chunks of stuff stuck in your elbows, or your PVC burns because the PVC doesn't have any lubricant next to it. But there's a lot of different ways around it that you can make it work. It's just, again, these are some of the side effects that can happen if you decide to be creative or try to improve your output from your blending system. So the last thing I have is kind of a survey of some different formulations. I think rather than going into them too deep, what I kind of want to promote is the idea of what changes as you go through these things. And so for me, something that's important as we look at rigid weatherable lineals and capstocks, you see acrylics become more important because impact strength is important. And you see that TiO2 becomes important because weatherability is important. So something is going to face the exposure of outdoors. We see TiO2. And typically the impact modifier can be important, not just for the initial impact strength to pass whatever specifications are needed by the siding industry or window industry, but don't forget that after it ages, things become more brittle because the PVC is breaking down. And so it does help maintain, with a stress concentrator in there, your mechanical properties after aging as well. You don't want to be able to, have a golf ball hit the side of your house and have a hole go straight through it. You want it to bounce off, maybe leave a dent at the worst case. Same thing for substrate. Now we're changing from going to weatherable. Now it's covered by a capstock. We're less worried about the exposure to UV. The titanium dioxide becomes less of an issue. The calcium carbonate content goes up. All right. So basically, how much can we put in and maintain the mechanical properties we need for the specifications of whether it's fence and cell class, vinyl siding for ASTM D3679, any other areas where you're looking to maintain that basic load of impact strength. You can see some with and without impact modifier, different levels of impact modifier. All right. But the other thing I'd point out is your tin, if you're going from weatherable to non-weatherable, something that has a high level of tin to make sure you protect it during processing, or maybe you're not so worried about the color at the end and you can get away with something that's like a pipe stabilizer with less tin, but gets the job done and still has a nice article at the end. PVC pipe, this is nicely set by the TR2 for anything that's NSF listed. Typically, when we see acrylic come in, it's in stuff like foam core pipe or fittings where you have a specialty need for a little bit more boosted impact. But over the years, pipe uses the most PVC resin in the industry. I think it's like 60 to 70%. And you'll see that it's that basic formulation I told you about: PVC, stabilizer, lubricants, a little bit of pigment and filler. That's all they need to make this stuff work for your potable water needs. All right, and then I think the last area it's kind of neat is cellular PVC. Here's where you start looking at all the things that have been developed through different technologies. molecular weights of process aids, typically from 5 to greater than 10 million grams per mole. And you're just trying to basically go through the application of the foam. Is it a deck board? Does it need to be weight bearing? What's the density for that? Is it a trim board that's wood replacement? What's the density of that? What's the cell structure look like? What's the thickness? This tells you about how you can gauge different molecular weight process aids to be used. And then basically for a foam formulation, you'll see it's highly geared towards fusion. So you have internal waxes, maybe an ester-based lubricant, the calcium stearate, a high molecular weight oxidized polyethylene, and acrylic. This thing's going to fuse immediately, right? And essentially, you're just trying to dial in what the properties are of the cell structure and make something that's a good building product at the end. So I'm going to stop there and kind of open it up to questions. Again, contact information here for me and Robert and Eric, our tech service person in North America for a lot of these applications. And just a reminder for everyone on the next workshop we're going to do with SBE on acrylic impact modifiers specifically.
Thank you, Kevin. Let's take some questions from the Q&A window. The first question, what is the typical range of percent crystallinity for rigid PVC, and is it possible to adjust this in processing?
Yeah, so I think that I looked back in notes at this actually in the days before this, and I saw, I mentioned Bob Paradise. I know something he had given was something from 4 to 10%. I know I've seen as high as 17% for the crystallinity, but really you're talking about a minimum amount. So this isn't like PLA where you can actually use the crystallinity to drive the mechanical properties to a totally different level. It's a minimum amount, but that minimum amount is what you're trying to reorder when you do the correct amount of gelation and get the mechanical properties. So I think maybe 8 to 10% is kind of like a happy high range for what you would see. And just so you're aware, there is an old, people still use it, I know it's still active, way to do DSC analysis, where you basically go through melting the primary crystallites, melting the secondary crystallites. You could take your process PVC, and actually it'll tell you what your process temperature was and how much crystallinity you put into the material. So there is a methodology to do that, and you can actually gauge it for yourself if you're having issues and want to perfect it.
Okay, next question. At high level, can you go over the mechanism of gelation fusion for a flexible PVC effective plasticizer?
Yeah, so when this is one that I think in one of the SBE final texts, somebody did a really nice job of this, and I probably should have included something around it. Basically, the plasticizer coming in helps to swell the PVC once it's there, and so the breakdown I think is essentially easier because you've actually started to do that process a little bit. So what you'll see in flexibilized formulations is you won't see a lot of acrylic, and you won't see the paraffin wax and calcium stearate because often too it's also transparent. And so that process already actually has kind of started, and I think it enables basically the molecular interaction to be possible to much lower shear. And so it's overall just easier, but the same mechanics are applying. You're breaking down the PVC particle, opening up the primary particles, and then trying to engage entanglement to the level you can with the amount of plasticizer. And semi-rigid might be 20 pHr, flexible, I was talking to someone just this morning about this, is probably beyond 50 pHr plasticizer and then way beyond.
Okay, next question. This talk is focused on powder formulations and can be applied to pellet compounds, but can you discuss any differences?
Yeah, I think, when we talk about injection molding in the lab, in our lab in King of Prussia, we often want to injection mold parts for customers to do testing for them, and we have to pelletize it first. I have done some powder injection molding, but it's really not a great idea. Typically what we'll do is we'll make some kind of pellet first. And so built into what you're doing when you make a pellet is you have to assume that you've already started the gelation process. So what might that look like? You might normally process a window profile at 180 degrees C, put it through your twin screw extruder and get a really nice part. Now you want to make a pellet to make a PVC compound on a single screw extruder that can't do quite the amount of work from powder. So you might process your pellets. Sometimes we might use a temperature of 140 to 160, get the pellets made. We know it's not fully fused and processed for the ideal range. Then you put it into the single screw extruder and you can make the next part, or you can put it in the injection molder, and that does the rest of the processing and adds the rest of the heat and shear you need to get to the best possible gelation phase. So it's all about kind of understanding, where you need to be based on the equipment for the pelletizing and what the final process will be to take you the rest of the way for the mechanical properties you need.
Okay, next question. Are there effective tests that will determine the degree of fusion in a post-extruded part?
Say that again, Deb. I'm sorry.
Yes. Are there effective tests that will determine the degree of fusion in a post-extruded part?
Yeah, so the main one I talked about was the DSC. So that ASTM standard for DSC and finding basically the processing temperature and percent crystallinity, that's probably the most fundamental way to do it. Now, if you want to test what your fusion is and you have an application where, say, impact strength is important, honestly, another way to do it is try some different settings and just do some drop dart and see where you get, and see where you are below where you want to be, where you pass through the optimum, and where you then fall off on the other side, whether there's too much heat and torque. So you can kind of make a nice process window study for yourself. When I first started in PVC, one of my first projects was to take a 2-roll mill and take temperatures every 5 degrees, and then take impact modifier at different levels and basically do a DOE and make plaques, and then make ISOT bars from those plaques, and then essentially make a process window for this formulation and type of impact modifier, and essentially dial in, hey, when you process at 180 and you use 4 PHR, you're going to get the best results. And I could basically map the whole thing out. So that's an applications way to do the same thing that you can get from the DSC data.
Okay, next question. How does regrind affect the gelation of the PVC compound?
Yeah, so that's a popular one. I think what you would find is that it's typically not helpful. The thing to remember about regrind is that it's already been processed through the main process once. But in reality, because you're using regrind, that means I think 6 to 7 iterations of the material that have been processed exist within that regrind too. And so you can imagine that you've probably passed the optimum of where you want to be for the gelation and processing of that PVC article. So the more you incorporate, the torque may get higher, the amount of work you have to do to get the final part fused well may change. And so typically what we're looking at is hoping that your balance of lubricants are keeping things from burning too much with the addition of the regrind, especially if it's beyond like 30% or 50%, and you're managing the torque as well you can and still getting the good mechanical properties on the other side. So yeah, it has a huge effect from that point of view. And Deb, I just want to interject. I see Aaron has a question on Silica foam, just to catch him here. On the differences between free and Silica foam, one thing I would say, Aaron, on that typically is because Silica, you basically have a calibrator that you're foaming into. We think about foaming sometimes from the outside in, and I would say not a lot typically changes for me there, except on the outside of that foam, you make a skin. And that skin and how thick it is based on how your formulation is kind of developed and how important that is to the final customer. And if you're putting a capstock on top of the Silica foam as well. So typically for a free foam, you'll still get a skin, but basically you're going to moderate with the rolls. And then when it comes out eventually, what that thickness will be with the blowing agent. On a Silica, you're worried about how thick that skin's going to be, what your target density is, and making sure it foams the whole way to the center, and so you don't have voids. And I would say there, I for the most part have seen lower molecular weights versus the ultra high be more successful in Silica because it can control that process a little bit better. But I would say nothing's impossible because I'm sure you could dial everything in. But those are the key concerns I have with Silica, is what that center piece looks like, and then how thick that skin is and how important that is for your application. And then Spence, I will see a semi-rigid. So I put one in here for semi-rigid as one of the formulations before I stopped. And I would say that, you know, the main difference here is you start to introduce stable or plasticizer, obviously. And as we're introducing plasticizer, we start to change diffusion profile. The other thing we might do is we start moving to different levels of transparency. Here's where MBS and acrylic mix becomes important in how you modify, and where you see, really for me at least, the package for stabilizers and lubricants change, because now you have to worry about the transparency as well. So those are the main changes for me, but this is the slide I had for that.
Okay, there was also a comment, regrind will also cause problems on DSC analysis.
To be honest with you, I've never done that, so I would assume it will. I don't know what kind of an artifact it'll give you, but you know, if you think of incorporating the regrind and making a homogeneous polymer at the end, honestly, if you do DSC on the full PVC article, including, you know, the regrind and whatever else is in there, if you've done a good job processing and you have a homogeneous melt at the end where there aren't, under microscopy, clear macro regions or, you know, microstructure of the regrind pellets themselves that aren't broken down, my guess is you should get some indication of, still get the process temperature and the level of secondary crystallites that are formed to give you an idea what gelation is in the full compound. So I think it would be a neat thing to run. And if you do, I would certainly encourage you to talk at Vinyltech about it and tell us what you find, because that's interesting.
Okay. Next question. I run a compounding plant for flexible PVC, today only using stabilizer lubricant 1-packs. I generally want to modify gelation percent after compounding. I have capacity to use one new raw material. What additional additive would you suggest for me to use to increase or decrease gelation percent? Wax, stearic acid, acrylic, etc.
Oh man, that's like that opens up a black box there. Yeah, so I would say the first thing is the 1-packs, I think, do represent a pretty unique challenge for formulators. Compounders, you know, especially want to have the ability to tailor things whenever their customers come to them and say that, you know, something's not quite working right on my equipment. I'd really like this to have more melt strength or fuse faster for me. You know, I would say in the flexible world, I think you're right. A 1-pack of stabilizer and then lubricant, or sometimes those things are combined, are pretty typical. And then the plasticizer, obviously, in PVC. I think the most common thing I see after that, again, this is not me being a acrylic guy, but probably would be acrylics, because the thing you could use with an acrylic is you could decide the functionality. Do you want it to be a lubricating process aid that gives you metal release and a little bit of fusion control? Do you want it to be something that's a mid-molecular weight process aid that can give you melt strength and you can tune the use level for gelation purposes? And again, you can still maintain clarity with that as well. So if clarity is something that's important to you, that's the other thing you're thinking of when you're adding this, is to go across all your formulations in a universal way. So I would say probably an acrylic is the thing that might help you tweak things, but I guess it would be application dependent too.
Okay, next. Can you talk a little more about the difference in volume-based versus mass-based loading of a brake bender? Do you see issues with torque readings when doing volume-based if there are shifts in bulk density?
Yeah, so this is kind of a problem of your own creation if you do it, right? So I think the important thing for me is that you measure the bulk density of your compound and know what it is. The plants that I've been in who are really successful with QCing when things start to go wrong, they measure the bulk density of their silos and the blends going into their silos and keep a library. And it just lets them know when things start to shift, if something's off. Maybe they were pushing the blending order too hard and it led to a difference, because they do use some kind of control to feed the twin screws, and you start to see a thinner part. Maybe things aren't foaming correct on a foam line. Maybe the gauge on the wall thickness for certain profile parts that are sensitive start to go out of whack. when I take that all the way back to the bray bender, it really just matters what your consistency is. So if you are comfortable that the compounds you use and the range of formulations you use will always be within, say 65 grams is just a good, like, rigid weatherable formulation, to add to a bray bender that I see a lot, right? That's always somewhere around 100 cc's, and that you're not going to deviate much more than 0.2, 0.3, 0.4 grams away from that, no matter what you do, then you can add 65 grams every time. What I say, typically we watch for in our lab when we do testing is, I want to know what the bulk density of the compounds is, just because our customers all have such different formulations. I want to make sure that I have an idea if something's really out of whack. If somebody's at 58 grams instead of 65 for their window profile formulation, geez, that's different. We should make sure we monitor that when we're testing specifically for them. Maybe let them know that we see that's different. Is there any idea why? So it's really just coming down to your, consistency and comfort level, and then also what translates to your production. So I just encourage everybody to take a look at what it is per 100 cc and do that bulk density test, and keep track of it and see where the shifts occur. If you always use a set weight to do your bray bender work and it's consistent on the bulk density, you're fine. If you always use 100 cc's, it's fine. What's fun is take a random, take 65 cc's and take 100 cc's and run the two next to each other, and you can kind of see how the diffusion curve will change. And that can give you insight into the one that you want to use, but tracking it is important. Yeah, so I think thanks everyone for joining. Like I said, I know that we're probably coming close to a time where people are going to be back out there. Purpose here for me was to re-engage with some folks, and if there's new people coming into the industry, I know that it can be hard to jump in, especially when you're not able to reach out and see things in plants and meet people. So, the one coming up in July with Rhiometer will be around impact modifiers, specifically in core shell technology. Definitely attend. You'll find and learn a lot about some of the things we talked about here, but in more detail. And it's a chance to, again, just ask some questions you might have, get some people introduced to technologies that may not otherwise have seen it. And for all of you that are carrying on in the PVC during this year, especially with everything that's happened, hang in there, and we look forward to seeing you guys soon as things open up and we engage again and discuss problems we're having together. Okay.
Thank you, Kevin, for an enlightening presentation. We'll be posting the presentation and recording in the SP library, and you also receive an email with a link. Please be sure to check out our upcoming webinars and have a fantastic day.